So this lesson is about roots and factors over the complex field. And the first thing I need to do is actually need to remind you guys about some stuff from algebra or intermediate algebra. You should recall that if we had a polynomial, if you had a polynomial p of x, if you had a root of 3, it meant that one of the factors of that polynomial was x minus 3. Right? If you had a root of -2, it meant that you had a factor of x minus -2 or x plus 2. Right? And it effectively means that, if you've got a root of 3, then x minus 3 will divide into p of x. Right? I suppose I should mention, by the way, what does it mean that this is a root? That statement means that when you plug 3 in, you're going to get 0. This statement here means that when you plug -2 in, you're going to get 0. Right? So this lesson is supposed to be about roots over the complex field. So what happens if now I'm talking about a polynomial, let's say a polynomial q of z. So it's not, one that you're necessarily plugging real numbers into, but maybe complex numbers. What happens if one of the roots is 2 minus I? Right? What does that mean about one of the factors of the polynomial? Right? Well, it should mean that z minus 2 minus I, in other words, z minus 2 plus I, will be a factor of that polynomial. Right? Similarly, if, and actually we can do this the other way around. Suppose that someone told you that one of the factors of the polynomial was z plus 3 minus I. Well, that would tell you that one of the roots would have to be -3 plus I. I mean, the moral of the story up here is that whatever the root is, you have the opposite of that after an x. So down here, whatever this root is, you have the opposite of that following a z. So whatever the opposite of this is, that's what the root is going to be for that thing. So long story short, if you've got a complex root, you can write a factor by doing z minus that complex root. If you have a factor, just think about what has to be subtracted from z, and you can come up with what the root is. So this leads us to the next concept, which is the complex conjugate root theorem. And the deal is there, and I've got it written here. If p of z is a polynomial with real coefficients, by the way, that's important. This is only true if you have real coefficients. So if you have that, and a plus bi is a root of the polynomial, then its complex conjugate, a minus bi, will also be a root. And therefore, z minus a minus bi and z minus a plus bi are both going to be factors of that original polynomial. Hope that makes sense. So it's sort of like if you already know that one of the roots is, 5 plus 7i, automatically, because of the complex conjugate root theorem, you know that 5 minus 7i will also be a root. But we also know about factors then, right? We know that z minus 5 minus 7i will be a factor, and we also know that z minus 5 plus 7i will be a factor of that polynomial. So I've got some examples that follow this coming up, so here they are. So if p of z has roots -5, 3 plus I, and -5 minus 3i, find any additional roots of p of z. So what that sort of means is like, okay, so we've got -5, yay, good deal. Because that's not complex, we don't do anything with it, right? But here, we have, 3 plus I. That means we should also have 3 minus I as a root, right? Similarly over here, if I have this root, we know that we're going to have its complex conjugate, -5 plus 3i, as another root. And so what that means is, it means that p of z has degree of at least 5, right? We had the real root, we had these two complex roots, and each one of them came, bundled with a second complex root. And so we're going to have at least 5 terms. If somebody had asked you to write down what this polynomial is, think about that for a second. How could you compute p of z? How could we figure out what p of z is? Well, we could write these factors. The root of 5, negative 5, would become z plus 5. The root of 3 plus I would become z minus 3 minus I. The root of 3 minus I would become z minus 3 plus I. By the way, before you start freaking out, I'm not going to have us FOIL this. Your negative 5 minus 3i would be z plus 5 plus 3i, and your negative 5 plus 3i would be z plus 5 minus 3i. And you really wanted to foil these two, mega foil these, ultra foil these. You could put the whole thing together. I'm not going to worry about it right now. That's the idea. The last example I have here is, so in this case I actually do want us to find the polynomial of the lowest degree that has these roots. So similar to what we said in the previous problem, this 3 is going to give us a factor of z minus 3. This root is going to give us a factor of z minus 1 plus 2i. That root, though, automatically also comes with 1 plus 2i, which means I'm also going to have a factor of z minus 1 minus 2i. Okay? So now, I need to FOIL these things together, and please, please, please hear this recommendation. Please, when you've got these things to multiply out, multiply together the two things that are complex conjugates. And actually, I've got a little bit of a secret here for you. This is a really, really neat trick. I don't know, one of my previous students in a previous year sort of noticed this, and it was a great trick. You may be looking at this thinking this is going to be like a 9-part FOIL kind of thing, like you're going to have to distribute the z to all of these, and then the negative 1 to all of them, and the 2i to all of them. I'm going to need to use a different color for this, and this may get confusing, but watch carefully. The secret is, look at this as z minus 1 plus 2i, and z minus 1 minus 2i. It's like, in secret, this is a difference of squares problem. When you FOIL this together, you're going to get z minus 1 squared minus 2i squared. And if you need to, pause the video and think about that for a second. But what I'm effectively saying is, I'm saying that part there is really just something plus b times something minus b, and we know that that's going to distribute together to give us a squared minus b squared. And so the reality is that thing can easily be FOILed out. I mean, this is just z squared minus 2z plus 1 minus 4i squared. Okay, well, that just means plus 4. This is going to be z squared minus 2z plus 5. And now I just have to multiply that with the z minus 3 that was there from the beginning. When I FOIL this whole thing together, I'm looking at z cubed. That's minus 3z squared minus 2z squared, so that's minus 5z squared. Then plus 6z plus 5z, that's plus 11z, and then minus 15. This is the polynomial of lowest degree that has those two roots. Okay? That's the end of this video. Those are the end of the examples I have. There's more coming in the next one.